Okay, I think we're ready to start. This session, I will talk about the last technique of integration. I mean, last for, of course, for us, for our syllabus. This is section 7.4 and is the integration of rational function by partial fractions. Okay? That means this is the last method for us, and let's see what it is. It's okay, I can go through, because as always I would like to squeeze the entire section in one sentence. Okay, let's see what we have. Okay? If you have any question, of course you can use the chat box. If not, you can just follow slide by slide. Okay, that means what we have. We do have rational functions, and we do have different types of rational functions. Then respectively, we will have different types, different kinds of integration, each of this kind. That means let's see what I have as an introduction. A rational function, like a fraction, we can say, it's like a ratio. If it's complex function, we may try to rewrite as a sum of the simpler fraction. Okay? That means this is the point to have simpler like a simple fraction, and we will call partial fraction. Okay? This nice simple fraction, it is the partial fraction. We definitely know some of the rational functions, and let's see. I can show you this. You probably remember them. As soon as we have like a fraction, like a ratio, then we will call a rational function. That we can see each of this integral includes the fraction bar. Of course, 1 over x, the simplest rational function, we know that the integral, natural log of x. If we have a little bit more expanded form, but still the linear function, we can still say natural log of denominator. Number 3, of course, that's different story. It's x squared plus 1. This is inverse tangent. And number 4 is just the chain rule, or if we prefer to say U substitution, of the form 3. That means 3 and 4 are almost the same thing, but we do have extra inner function. And number 5, it's the also including the inner function, and it's the more complex form of number 1. Yeah? That we can still say natural log of the denominator. We can see natural log of x, but we do have to see derivative of the denominator. And the U substitution, of course, will work. Or if you remember this formula number 5, it's still fine. Okay, that's we can see we do have rational functions, and we still have to remember, because now we will see lots of rational functions, even more complicated, like numerators. They're not gonna be just one, like for the first 3 integrals. We will have a proper rational functions. So let's see what we will do. First of all, let's talk a little bit about the simple fractions, partial fractions. So I will take actually 2 partial fractions, simple fraction. 2 over x minus 1 plus 1 over x plus 2. That means I'm saying that's the simple fraction, because it's just the linear x minus 1, x plus 2. I can't like simplify them. The denominators, I can't simplify them, I can't rewrite. That's the simplest form. But what I will do, having these 2 fractions, I will try to combine them together, which means I need a common denominator. I will multiply the first fraction by the numerator and denominator by x plus 2, and the same for the second one, but multiplying of x minus 1, x minus 1. Okay? So we can see we do have a common denominator. I can rewrite as a 1 fraction, like just copy 1 time the denominator, and the numerator is, I did distribute 2, okay, and then we have 2x plus 4, and x minus 1, adding like terms, 3x plus 3. And maybe one more step, I can distribute everything. I can FOIL the denominator. Okay? That we can see this fraction, the boxed one, it's not a simple fraction. It's not a partial fraction. It's a nice rational function, but we know where this comes from. That means now the point is, for example, to integrate this function. Okay? Integrate this rational function. That means if you will see this type of rational function, like what we can do. We may try the U substitution, but probably will not work. It's definitely not the trigonometric substitution. It's definitely not the good function for the integration by parts. You may always try, but you will probably, by practicing, you will know that that's the rational function. And what we have to do, we have to rewrite this function as a sum or the difference of the partial fractions, the simpler fraction. And of course, I know that this is equivalent to this. Okay, because we can see if I will come back, I do have that form. Okay? Of course, I don't want to mess up everything, but we can see both of these boxes are equivalent. And that's what I did. And now, having this simple fraction, let's see how easy it is to integrate. 2 is a constant and just ln of the denominator. 1, just ln of the denominator. And that's it. That means this is the point. As soon as we have the simpler fraction, or we can call partial fraction, it's no problem to integrate. But the question is that step. Of course, I didn't cheat, but I used the given fractions. Yeah? Because I'm assuming that everyone can make a common denominator, and having a simpler fraction, you can definitely combine them together and create a rational function, like a complex rational function. But having this complex function, how we can get this partial fraction? Yeah, that means that step, this question mark, is the job for us. Okay? And I will try to show you, I will show you how to do this. Okay? How to get partial fractions. Okay, that means let's start. Actually, we can even start with this, because what I nicely divide each rational function by like different types. And I can show you, and we will have 3 different types of integration, 3 different types of rational function. But let's take this one. I will explain, I will tell you what is the name and what is the kind, what is the case in a minute. But let's see, because it's really similar what we just did. Okay, that's what we have. We have rational function x minus 7 over x squared minus 6x plus 5. And we know that we can definitely rewrite this as a simpler fraction. One thing is important, that this rational function is definitely a proper rational function. Yeah? I have a definition in a few slides later, but proper means that the degree of the denominator is greater than the degree on the top. It's like a proper fraction. Yeah, like if we have, let's say, 1/2, 1/3, or 2/5, these are the proper fractions. As soon as I have 4/3, of course, we can rewrite this as a mixed number. It's a 1 and 1/3. Yeah, that we can see. Always when the number is smaller on the top, it's a proper fraction. And the same we can apply for the function. If the degree of the denominator is greater, then we have a proper rational function. If the degree on the top is greater, then we have improper and we need additional step. But this is fine. We do have a proper rational function. Now, the degree of the denominator is 2. That means I am thinking that I can probably, I will expect two partial fractions. But the first thing is I have to try to factor out denominator. And do you think you can help me to factor out? That's my first question. It's x squared minus 6x plus 5. Okay, what are the factors? X minus 5 and x minus 1. That I'm just copying this from the chat box. And I believe that's correct, because negative 5 and negative 1 will give me 5 when I multiply, and negative 5 and negative 1 adding together is negative 6. Okay, I switched the order, but okay, that's what we can see. That's what I did. Yeah. We do have a factors. And one more time, I can split these factors because that's the product of both of them, which is the common denominator. That means I am assuming that these two fractions are the partial fractions. Yeah? You may notice I am missing these numbers. Okay, let me come back for 1 second. Like, do you see this one? This one we end up having 3x plus 3, but it's no indication that I will have 2, the quantity 2 over x minus 1 and 1 over x plus 2, like 1 for each. That means we have to find out what is this number and what is this number. And at the moment, I just name it A and B. Okay, that means this is we have to know how to find the quantity A and B. What I can do, I can still try even without having the exact A and B, because they're going to be constant. I can still try to integrate this, because this is just A, I can put on the side, and ln of x minus 1, plus B, I can put on the side because it's constant, and ln of x minus 5. Yeah, that means you can see I almost integrate. I mean, not almost, I did integrate my rational function, but I'm missing the two important numbers. But you can see how nice, yeah, and easy is the process. But the point is to know how to find A and B. That means let's do it. I will show you. That's what we have. Let's come back first. Yeah, I can maybe remove this. Let's come back and let's look at these two steps. That we have x minus 1 times x minus 5. Yeah, that means denominators, if I look at these two fractions and try to combine them together, okay, I can actually even write it down. Oh, let's just do just the fractions. Okay, how am I writing? X minus 5. That means this is 1. And then I do have A and B, x minus 5. And I would like to match my right-hand side to the left-hand side. That means I will try keeping my A and B to get the common denominator again. That means the common denominator is x minus 1, x minus 5, and A, we have to multiply by x minus 5, and the coefficient B, we have to multiply by x minus 1. And I can copy this one more time, because this is the way to find. And now we can nicely see denominators are the same. So the numerators, they also have to be the same. And I'm saying that x minus 7, it's the same, must be the same, like A times x minus 5 plus B times x minus 1. Okay, and now I will focus on that equation, and let's see what I can do. We do have two ways to find A and B, okay? And I will show you both of them, but let's start with the first one. Okay, the first way is, for example, to pick a value for x. That means I will pick maybe 1. Let's assume that x is 1. And let's substitute that 1 to the blue box. 1 minus 7, A 1 minus 5, b, 1 minus 1. Okay, excellent. This is gone, that's 0. This is negative 6, negative 4a. And then a is negative 6 divided by negative 4, it's 3 over 2. I do have the quantity a. Yeah, we can see how nice and easy. Now, I still have the quantity b. That means I will pick for x5. Okay, and let's see, and let's substitute 5 to the blue box. 5 minus 7, a, 5 minus 5, b, 5 minus 1. 5 minus 7 is negative 2, that's 0, and 5 minus 1 is 4, b. b is negative half. I divide both sides by 4. Okay, done. Now we can see, that means this is the way to do it. Can you tell me like why I pick 1 and 5? Do you see some consistency? Because they will always cancel out one of the coefficient a or b. They are simply zeros of the denominator. Yeah, and the roots of this equation. Okay, and now I can show you this, and the final answer is 3. Oh, my pen is 3 halves ln of x minus 1, and then, oh, actually minus 1 half ln of x minus 5, and plus the constancy. Okay, yeah, but we can see that's the way to rewrite as a partial fraction and find a and b. Okay. Now, let's look at a little bit of the terminology and definition. That means this is just what I said. We may have a proper rational function and improper rational function. And everything what we will do, because I will cover 3 different cases, and the integral that I just integrate was the case 1. But all of the cases, case 1, 2, and 3, I will always refer to a proper rational function. We always have to check if we have a proper function, which means degree on the top is less than degree on the bottom. Okay? Now, if we actually end up having improper rational function, then we have to do one extra step. Okay? We have to perform the long division. We have to divide polynomial from the top by the polynomial from the bottom, and then we will rewrite as a quotient and the remainder, and still the denominator, the divisor. Okay, like for example, like let's just the numbers, like if I will have 12 over 5, yeah, that's not a proper, that's improper fraction. And if I will divide 12 divided by 5 is 2, okay, well, let's say 13, because I don't want to repeat the quantity 2. 13 divided by 5 is 2, yeah, that's the quotient. And then what's left? 3 over 5. Yeah, that means that's what we will do with the polynomials. Okay? Remember. And then this will be a proper rational function, and then we can follow, we can investigate if it's the case 1, 2, and 3, and then solve it. Okay, that means let's do one of them. Oh, don't look at this. We have x cubed plus x over x minus 1. And what do you think? It's a proper or improper rational function? Of course, it's improper, because cube is definitely greater than the 1. Okay, that means what I will do, I will take x cubed plus 0x squared plus x. Yeah, please notice that's the polynomial from the numerator, but I did put each degree, each term, the squared was missing, and now I will divide by x minus 1. I mean, let's see. Hopefully we remember the long division. X cubed divided by x is x squared. Okay? And then we have to multiply back. I will multiply x squared times x squared times -1. X squared times x is x cubed, but I will subtract. X squared times -1, it's negative x squared, but I will subtract, then I'm changing the sign. X cubed minus x cubed, it's gone. 0x squared plus x squared is just 1x squared. And I can drop down this last number x. Okay, I think I can still divide because I have x squared and x. That means I can still divide. And let's follow the same process. X squared divided by x is simply x. And now I will multiply. X times x is x squared, but I will subtract. X times -1 is negative x, but I will subtract. I'm changing the sign. This is gone. X plus x is 2x. I can still divide. 2x divided by x is 2. 2 times x is 2x, but I will subtract. 2 times -1 is -2, but I will subtract. 2x minus 2x gone, and 2 is the remainder. Right? That means now I can rewrite my function. Yeah, we remember quotient plus something what's left, yes, the remainder over the, we have different notation. I call quotient. Okay, I can call just maybe, because I think I was gonna put, but I like this as a Q. Let me put K. Okay, this is K dx. Oh, no. That means what we have. Quotient is, of course, that part. That's quotient. I can even follow my colors. That's the final answer. Okay, that's we have x squared plus x plus 2, yeah, when I divide, and then plus 2 is this one, is the remainder, all over x minus 1, because I can't divide 2 by x minus 1. Okay, which this is, I can use maybe blue. Actually, do you know what? I don't even have to introduce new letters. I can just call this x minus 1 because I don't have to. Okay, that means now we can see the point is to do the long division, to have the entire thing like the quotient without the fraction, and we will still end up with the rational function, but it will be always proper rational function. Okay? And now I think we have we're lucky, we have simple, we have like a partial fraction which we can integrate right away. Integral of x squared is this, integral of x is this, integral of 2 is just 2x, and integral of that part is a constant 2 and ln of the denominator plus the constant of integration. Okay? But we can see that's the process. If the function is rational, improper rational. Okay, now let's focus on the 3 different types of proper rational function. Okay, that means what is the next step? Okay, the next step. If we have the proper rational function, we will always look at the denominator. Okay, that means that's the next step. Having proper rational function, we looking at the denominator. And we have to try to factor out as far as possible. Okay? We may have all of the linear factors, That's what we just did. Or we may end up with the factors that are not like quadratic one, irreducible, that we can't reduce further. Right? And for example, let's say this is the denominator, x to the power of 4 minus 16. Then we can try to factor out, and we can see we have x squared minus 4, x squared plus 4, and x squared minus 4 I can still factor out like x minus 1, x minus 2, x plus 2, but x squared plus 4 is irreducible. We can't reduce this one. Okay? That means that's what we will do. We may end up with the linear factors, or we may end up with the irreducible quadratic. Okay? But that's always the next step. Check if the function is proper, and now factor out denominator. And now let's see. Case 1, finally. Okay? If you factor out denominator, and you will see that all of the factors are the linear factors, and none of them is like repeated. Okay? And of course, none of them is the constant multiple of another. That's mean what we have. We took the denominator and we simply factor out, and each factor is the different linear factor. Okay? That means that's actually what we did. This is case 1. Okay? Not the easiest one, but one of the simplest one. Each case is different, and each case could be recognized as an easy. Okay? So, for example, yeah. We will have, and then yeah, I did type a sub 1, a sub 2, a sub 3, but having each of these factors, okay, in the denominator, we can split for the partial fraction, and we can, of course, we can call a, b, c, I don't know, e, and if we even need more. Okay? For it's just easier for me to have the systematic name, but we will always put a constant. That means we will know how many, based on the number of the factors, we will know how many partial fractions we have, and we have to find a, b, c, d, and so on. Depends on the number of fractions. Okay, that means let's solve one more integral, which represents case 1. Okay, 5x minus 1 over x squared minus x. Now we can definitely see it's a proper, that means we good, we don't have to do the long division, it's a proper rational function, and it's definitely, I believe it's a case 1. Because can you tell me how can I factor denominator? Do I really have a linear factors? Yes, thank you. That means I have x and x minus 1. Both of them are the linear factors. No, I don't like that loop. I can't remove this. Okay, that's actually weird. Okay, I did. Oh, no. Okay, that we can see x to the power of 1 and x minus 1, which is also x to the power of 1. That means we know right away. Actually, I can ask you, how many partial fraction we will have? We will have 2. Thank you, Ryan. And that's simply these fractions, denominator x and denominator x minus 1. Okay, and now a and b. That means the job is for us to find a and b. I also type my answer, a times ln of x, b times ln of x minus 1. But we're still looking for a and b. And let's do the same way that I show you the first integral. Okay, but the important thing is this is the case 1. Okay, that means what we will do. I have my 5x minus 1. This is my numerator. And if I will combine these two fractions, again, my numerator with numbers a and b will look like this. A, I have to multiply by x minus 1. Okay. And then b, I have to multiply by x. Okay, that means that's my numerators. You probably notice I did skip all of the denominators. I just have to focus on this. Okay, and let's do it the same way. I will pick for x 0, And let's substitute this to the equation. 5 times 0, of course, is 0. 0 minus 1 is -1. And then A, I can put it 0 minus 1, and B times 0, of course, is gone. That means -1, negative A. Wow, really nice. A is 1. Yeah. Now, who can tell me what the next X value I will pick? Yes, what value of X shall I pick? I have to put 1. Good. And let's substitute. Oh, I can possibly call the same way. Substitute to the blue box, right? Because that's what I did for the first one. Okay, 5 times 1 is 5, minus 1. A will be gone, and then B times 1 is just B. 4 equals to B. That's 0. B is 4. Okay. That means the final answer is 1 ln of x and plus 4 ln of x minus 1 plus the constant c. One thing I would like to show you on the multiple choice, you may see that I will combine the addition of two logarithms. That means I'm gonna take that coefficient 4 here, okay, and then when I'm adding two logarithms, I can multiply the values. Absolute value, oh no, absolute value of x and times that part. Right? Because when we adding logarithms, we multiplying the inputs. That means just in case both of the last two lines are the correct answer, just different form. Okay, as we can see, the coefficient a and b, case 1, it's relatively easy to find. Okay, let's look at the case 2. And now, of course, because I did solve two integrals, but what I will recommend, you can check the list of integrals that I am providing in the midterm 1 module, and you can try to integrate as much as possible, okay? As many of the integrals as possible, because then you will definitely practice. You really have to practice this. You know the tool, you know the concept, but please do practice. Okay. Okay, I have another one, but I will not solve it. The only thing is we can try to, let's just set up the integral, okay? But I will not compute the A, B, or possibly C, because I would like to show you the other cases. But please help me. How can we factor out the denominator? Yeah, even if you're rewatching later the video, you can also try before I show you. We have 2x cubed plus 3x squared minus 2x. Right? That we can definitely see, right? That's my first step. We did factor out x. And do you think you can still factor out that part? Because we have coefficient 2, x and x. Yeah, like we still have quadratic, and I believe we can factor out. We can put 2 and 1, and then 2x will affect that 2. That means this is 4 minus 1 is 3. Okay, that means that's the linear factors. And we can see we had the third degree polynomial in the denominator, and we do have three different factors. And it looks like I will have three different partial fraction. That means you can do exactly the same. You can try to find A, B, and C the same way that I did for A and B, and just to integrate. Actually, I did integrate, and please notice this is just A ln of x, no problem. This is just C ln of x plus 2, absolute value. But since we have coefficient 2 of x, this will give me additional half if you will do the u substitution. Okay, that we do have 2x, but we need that half to divide by 2. I mean, divide by 2. But coefficient A, B, and C, you can try to do it, okay? But we will skip this. Oh, and I do have actually the answers for you. Okay. The same, this one, we will leave it. I have the general answer, but you can maybe just tell me, can you tell me what are the factors of the denominator? And then we will have A over the first one, B over the second one. Okay, and x squared, yes, thank you, Ryan, is x plus 3, x minus 3. That means this is the first and this is the second. And of course, I can say A times natural log of this plus B ln of this, and plus the constant of integration. And we know how to, you know how to do it, computing A and B. Okay. Now, case 2. That means case 2, what is the case 2? We're still looking at the denominator, yes, the same steps. We're trying to factor out, and we will still have all linear factors, but some of them will be the same. Some of them will be repeated. Right? And now we have to be extremely careful what to do. That means if some of them are repeated, we also have to repeat them in some way to create the partial fraction. Okay. Another thing is because since all of them are the linear factors, creating a partial fraction, you may notice we will still put just the constant A, B, C, D, E, or if we need more alphabet, we will use it on the numerator. Okay, that means let's see this, because that's sometimes confusing. Let's pretend that this is my integral. Okay, that means, actually, I don't even have to. That's my rational function. We can definitely see that it's proper, because this is cube, and this looks like the square and cube. When I will FOIL, I will have x to the power of 5. Okay, that means actually, yes, x to the power of 5, and then I will have the rest of the terms. Since I have x to the power of 5, each of the factor is actually, each of the factors are linear. That means I am expecting 5 partial fractions. Okay, 5 partial fractions. And you can, I did expand for you. Because what's happened, x squared means x times x. X minus 1 cube means x minus 1 times x minus 1, and of course x minus 1. Okay, but now we have to be really careful. I can't just say a over x, b over x, c over x minus 1, d over x minus 1, and e over x minus 1, because we can see that's kind of pointless. Looking at this, the common denominator will be just x and times x minus 1. Yeah, because none of them is taken. And I really need to see square, and I really need to see cube. That means what we will do to have the proper fractions. Since this is x squared, I have to have a fraction with x and then x squared. Okay? So let's say this will be x to the power of 5. Then I will have a fraction with the denominator x, x squared, x to the power of 3, x to the power of 4, and x to the power of 5. And of course, I can put my alphabet. Okay? That means you can see, if let's say if this will be 5, we have to include every single power. Computing the coefficients A, B, C, D, and E, we may have 0 for some of them, but we don't know. Yeah? Because looking at these denominators, definitely the common denominator is x to the power of 5. And of course, I can work on my numerator. But please remember, we have to include everything. Okay? I can even write maybe x to the power of 5. Okay, now let's look at the second part, x minus 1 to the power of 3. That means I have to have denominator with x minus 1, x minus 1 squared, x minus 1 cube. Okay? You can see I have to include every single power and stop at the highest one. Again, maybe this will be 0. I don't know. Maybe this will be 0. I don't know. Oh, I'm changing. But I have to include all of them. Okay? Let's practice. I have one more slide to show you. Because we can see we may have partial fractions like that. Okay? And it's still the common denominator. The denominator, we can see for both of them, denominators are the same, but they came from different fractions, different sum of the fractions, different functions. That's we always, doesn't really matter, we will not know. We have to include every single denominator. Okay, let's try. Oh, that's quite long, but let's maybe solve this one. 3x cubed plus x squared minus 8x plus 3. And its denominator is x squared times x minus 1 squared. Okay? That means what we definitely have proper rational function, because that's cube. And if I multiply, I will have to the denominator will be x to the power of 4. Okay, that means x to the power of 4 is indicating that I will have 4 partial fractions. Okay? And we can see I have x, and I have x minus 1 and another x minus 1. Okay, that means let's see, that's my fractions. X and x squared, x minus 1 and x minus 1 squared. And the same thing, if this will be like 5, I will keep working. X minus 1 to the power of 3, x minus 1 to the power of 4, x minus 1 to the power of 5. Okay, that means now let's try to find A, B, and C. Or maybe we can integrate first. Did I integrate? Oh, okay, I didn't integrate. Because this one is interesting. This is no problem. A, ln of x, we will find A. I believe this one is not a problem. C, ln of x minus 1. Okay. But what about if we do have a square? What will be this integral and this one? Right? Let's maybe do on the side. If we have an integral 1 over x squared dx, do you know what's the integral of 1 over x squared? Who can tell me? Oh, no. This is x to the negative 2. That means no logarithmic formula anymore. I can simply apply the power rule. I will add 1. That means I will have negative 1 and negative 1. Negative 1 over x plus the constant. Okay? That means this will be negative b over x. This will be negative d over x minus 1. That means that's the only difference, because we kind of see the square. I mean, not kind, it's definitely the square. And plus, let me put k for constant. Okay, that means this is, and that's b. We still have to find a, b, c, and d. We will do it. Okay? But I was going to point out how to integrate 1 over x squared. Okay? And the same 1 over x minus 1 squared, the same thing. Okay? That means this is my integral. And let's find the coefficient a, b, and c. Okay, I will compare my numerators. 3x squared, 3x cubed. 3x cubed plus x squared minus 8x plus 3. Okay, now looking at all of these 4 fractions, I know that the common denominator is this, x squared, x minus 1 squared. Okay. But we have to adjust each fraction. That's mean what I have. For the first fraction, I have only x in the denominator. This indicates that I am missing 1 extra x and I'm missing x minus 1 squared. That means the quantity A has to be multiplied by x because I am missing that x to have x squared, and I am also missing x minus 1 squared. Okay, done. Now let's look at the second fraction. Second fraction, underneath b, we do have x squared. The only thing that we're missing is x minus 1 squared. Okay, now c. C has x minus 1. I am missing another x minus 1 and x squared. Okay, and D, underneath D, we do have x minus 1 squared. That means we're only missing x squared. Okay, excellent. Let's figure out. I will pick the value for x 0. Okay, and let's see what we can get. 0, 0, 0, 3 on the left-hand side, and then this will be gone, this will be gone, and this 0, negative 1b will be 1b. B is free. Yeah, nice and easy. Now, let's pick for x, of course, 1. We know why. 1, I have 3 plus 1 minus 8 plus 3. And this is gone, A will be gone, B will be gone, C will be gone, D times 1. Okay, that means D is equal to 6, 7 minus 1, negative 1. Nice and easy. But now the problem is with the case 2, that we do have more letters, more fractions than the zeros from the denominator because they are repeated. Right? 0 is repeating twice and 1 is repeated twice. That means now what we can do, we have to actually pick up any value of x, which we will not nicely simplify, but we will have extra steps to simplify. Okay, maybe negative 1, because I have to really pick the simplest value. Okay, negative 3 plus 1 plus 8 plus 3, that's the numbers when I substitute negative 1 on the left-hand side. And now we have to be really careful. You can watch what I'm doing. I am substituting negative 1 to our blue box. You remember the blue box. You may help me or you may correct me, but let's try. Negative 1 and negative 1 will be negative 2. Squared is positive 4, but this will be negative. Negative 4a. Okay. Negative 1, positive 4b. That's 4b. Negative 1, it's and negative 1 is negative 2c. And the negative 1 squared is just positive d. Okay. And I can try to simplify. Negative 4a. B is actually 3. I can substitute 3, which I will have 12 minus 2c, and d is negative 1. This means what we have? We have 4a plus 2c, if I move them on the other side. 12 minus 1 is 11, and 11 minus 9 is 2. Okay, I can divide by 2, but I can leave it for now. And now what I have to do, since I have another coefficient to calculate, because I have 4 of them, I have to pick one more number. And I think I will pick, I'm not fan of big numbers, but I will pick 2. And let's again watch me what I'm doing. 2 cubed is 8. 8 times 3 is 24, minus plus 4 minus 16 plus 3. And then 2 will give me 1, 2a, 1 plus b. Oh, it's not bad. 2, 4, 4c, and 4d. Am I right? 4 and 4. Okay, 24. Who can compute for me the 15? Okay, I will put 50 on the left-hand side, Ryan, right? Okay, shall I check? Probably you're right. 12, yes, 15, yes, thank you, thank you. Okay, and now 2a, b is 3, I can put 3, c, we don't have it, c, and d is -1, -4. That means what we will have? We will have 2a plus 4c, which I'm on this side, and this is -1, but I will add to both sides 16. That means now I will combine these two equations. Okay, I will put 4a plus 2c, it's equal to 2. Actually, let me divide. Oh no, I don't. Oh no, I can divide by 2. 2a plus c, it's equal to 1. I promise you will probably not have as heavy algebra. Okay? That means I will copy this. 2a plus c, it's equal to 1. And this one I will multiply by negative. That means I will have -2a, -4c, -16. Because you may notice I will add them together. A is gone. -4c plus c is -3c, and -15. C is 5. Wow. If c is 5, we just need a. I can put here. A could be 2a. It's 1 minus 5, -4, -2. Okay. Yeah, that means now it's simply, I can use maybe even blue color. You have to just substitute to this green box instead of a -2. Oh, okay. Instead of b 3, instead of d -1, and instead of c 5. Yeah, but I still show you how. I mean, I use the same method. I think important part is the blue box. Make sure that you understand how I create the blue box. Okay? You can probably rewatch again that part, and you can, it's just the common denominator, and it's probably algebra 1, but I know when we put all of this concept like from different perspective, we may think that it's challenge, but make sure that you know the blue box, and I'm sure the rest of them, it's not complicated. Okay, that means this is case 2. Yeah, you can see linear factors, but some of them are repeated. That's the problem, that we have a little bit extra steps. Okay, let's look at the case 3. Case 3, the same steps. You're looking at the denominator, you're trying to factor out denominator, and you will factor out, but some of the factors will be not linear factors. You will stay with the quadratic one. You will stay, hang on, you will stay with the quadratic one, which we call irreducible. We can't reduce further. And for example, this is a rational function, and we can see one fraction, one partial fraction, easy, no problem, okay? But the rest of them, the rest of the factors, x squared plus 1 and x squared plus 4, are the quadratic one, which we can't reduce. This means that we have to put them in the denominator, and this will be the denominators of the partial fraction. And now, please notice that as soon as I have quadratic one, irreducible quadratic denominator, then on the top, I can't just put constant, like a, b, c, d. Having a quadratic one, okay, I'm looking at this bottom, having the quadratic irreducible, I have to put a linear form on the top, like bx plus c, dx plus e, and so on. That means that's really, really important. Yeah? We can't put just A, B, C, D, and so on. Again, I'm repeating. As soon as you see the quadratic irreducible, put the full linear form. I think this is not easy to prove, but this must be set up this way. Otherwise, everything is wrong. Okay? Maybe I can check the appendix. Maybe they have proof, but of course, we don't even want to look at the proof. This just has to be like that. Okay, Jeff is asking, will x in bx plus c change if we have something like 2x? No, doesn't really matter. You may still have, like, let's say, I can even we may even have 2x squared plus 1. Okay? That's also irreducible. That means I will add 1 extra, and you will still have to put just the linear form. I think I know my alphabet, F, G. Fx plus g. That means no, we will not put extra 2. No. Yeah? Probably that 2 will affect the calculation, and this will have effect of the coefficient f and g, but we're not setting extra 2 right now. Yeah? If we will integrate, this is also different, a little bit different. That 2 will change something, but the whole integration process. But for the setting of the partial fraction, no extra 2. Okay, that means let's see. Oh, I don't know if I said that. I was thinking to do this. Irreducible quadratic factors, but none of them is the same. All of them are different. Okay, we do have case 4 if the irreducible quadratic factors are repeated, but we not cover in this class. Okay, that means only case 3 is the last one. And let's see. Perfect. Proper rational function because it's x squared on the top and x cubed in the denominator, and I can factor out denominator only this way: x times x squared plus 4. Okay, that means now we will have only 2 partial fractions, x, and the second one will have denominator x squared plus 4, and you can see I can't just put b. I have to put the entire linear form. Okay? Please remember, it's just different. Okay, and let's try to integrate this, and we will be almost done. Okay, I have the answer, but I didn't type the solution. Let's do the same thing. I may integrate keeping a, b, and c, but let's maybe find a, b, and c, and then we will integrate. And because especially the second partial fraction, we need like few extra steps. Okay, the numerator, 2x squared minus x plus 4. Okay, this numerator must be the same like this one when I combine the fraction. That means a, I have to multiply by this denominator because I already have x, and bx plus c, I have to multiply by x. Yeah? No problem. X squared plus 4, and then bx plus c, I will multiply by x. Okay, and let's do it. Let's find. Of course, I will pick 0. Nice and simple number. 0, 0, 4, 4a, and that's 0. That means a is 1. Good. And you can see we do not have more zeros of the denominator because x squared plus 4 is never 0. That's the reason that is irreducible factor term. Okay, we have to pick some. Of course, I will pick the easiest one, 1. 2 minus 1 plus 4, 5a plus b plus c, because it's just 1. And then this is 5. 5 times 1 is 5. b plus c. That means b plus c is 0. Or I can say b is equals to negative c. I need another equation, maybe negative 1. Let's see. 2 plus 1 plus 4, 5a, and then negative b and negative will be positive b minus c. 5, 7, 5 times 1 plus b minus c. That means we do have b minus c equals to 2. And b is negative c from the above. Negative 2c is 2, c is negative 1. That means if c is negative 1, then b is positive 1. Okay, yes? Yeah. Okay, that means great. Now let's see the integration, because it's just one extra thing. You still know how to integrate, but just in case. 1 over x. 1x minus 1 and x squared plus 4. Okay. Okay, this is just ln of x, no problem. But for the second fraction, I will recommend that you will split a fraction, split this function. We will say x over the denominator and 1, negative 1 over the denominator. It's still an integral. Okay, because now, let me copy this. This one, it's good for the u substitution. Yeah, you probably can see that if you will let u to be the denominator, you will have x to be cancelled out, but the derivative of the denominator is 2x. That means you will have extra half. But I will do my trick. I will put 1/2 and 2, yeah, the first slide, you can check. And I will keep this half, but looking at this, I see a function and its derivative on the top. Then, if I see this, I can say ln of the denominator. Okay, that means that's done. But as I said, you will get the same thing if you will do the u substitution, and I can leave it for you. Okay, and this one actually has no function on the top, I mean no x, and denominator x squared plus 4 looks like inverse tangent. Only 4 will affect the answer this way, half inverse tangent of x half, and plus the constant k or constant c, doesn't matter. Okay, that's when you can, please note that I did split this fraction for 2 of them, and then you will integrate separately. Okay, that means I will finish the session. Of course, we need tons of practice. Please check Practice with Kasia videos, because I will take each case and I will solve like additional integrals for you. Okay, like maybe 2, 3 for each case, because we still need practice. But you know all of the 3 cases, and now just practice. And I will recommend to check the midterm 1 module, and I think I gave you like a list of lots of integrals. That means please go through all of them. And next week, again, actually, I can put the video, just you will see me. Next week, it will be the review session. I will send an email on Monday, because maybe I can run the evening session. Maybe more students will attend. If you can't attend, still you can watch the session later. But I will run 1 review session, and the midterm will be open Thursday and will be closed Monday. Okay? That means please practice a lot every day, put lots of time, lots of hours, and then I think you will be good. But you have to practice a lot. Okay? And integrations are so nice. Okay, thank you. Good luck with your review, with your midterm review. Any question, anything, post on the discussion board or email me, and I will definitely assist you. Good luck, and thank you for joining me as always. Thank you, Ryan and Jeff. Thank you.